For next presentation, we have Vlatko. Is it Vlatko? In Croatia, it is known as Kost, or as we like to call him T-Bone. So, please.
Thanks. Hi, I'm Vlatko. I'm CTO at Iverto. We are like a cybersecurity company here in Croatia doing like a red teaming, blue teaming, purple teaming, all that stuff. And I'll talk about Linux improvements in memory corruption-based protections because there are some recent developments which happened just, I don't know, a month ago. And I think it's worth mentioning what's there. And I took some time actually to dig through all those things and mailing lists because in reality, you don't have any central place where you can read about this one because it's parts and pieces you will see later, which just you have to find something on the mailing list, you have something other on somewhere just written some patch, and then you have to join all this together to actually get something meaningful and useful. So I will talk about the overflows. Are they still relevant, right? Something about this Intel control flow enforcement technology, which is now in mostly CPUs. If you bought it after 2020, probably there is a chance that you already have it inside. And I will talk about the Shadow stack itself. And of course, there will be a takeaway for system administrators, developers, if you're a security specialist, whoever, I think you will find something useful. Also, I hope there will be some time for questions and answers. And why this, right? If you see Linux, it's almost everywhere, right? Not just on the desktop computers or servers, but it's also in the cloud. It's important because you have a lot of, for example, container workloads. On phones, right? If you have Android phone, I guess you are actually having some kind of Linux there on tablet, readers, remarkables, whatever, even on mainframe. And maybe this is the year of Linux on the desktop, right? I don't know. And yeah, on embedded stuff as well, different IoTs and so on, even like game consoles. So if you have something like, let's say, this, right? This is also Linux for gaming. You never expected it, right? And yeah, it even been to space and so on. So I guess anything that happens in security space here, it really have very big impact on security on many, many different aspects here, right? That's why it's worth looking at it. And how you can actually harden it. I guess everybody who knows buffer overflows, anyone here? Yeah, you know, you probably saw this slide, but it's just actually one of the techniques where you actually overwrite much more bytes than it's intended to, right? It's basic stuff. So I will not spend too much time on it, so we have more time for more stuff which our goal is. Anyone there to explain? So I don't have to? No? Okay. So in short, you have like a destination which is like 8 bytes, and then you just, what happens if somebody overwrites with something bigger, right? Standard basic stuff and so on. So the question is, hey, is this still relevant, right? What do you think? Can you raise the hand if you think it's still relevant? Okay. Yeah, we have. And who thinks it's not relevant anymore? Okay. So even if you are using some kind of a higher language, probably you are using some kind of a module which is actually written in C or C++. And if you're calling that function, which is vulnerable, you can still get bited by it, right? And you can still get affected by it. So until we all have everything written in Rust, right? Until that moment, I guess we still have the same problem. The only problem is it gets much harder to exploit it, right? Back in the days, it was really easier to exploit it, but now it's getting more harder and you need more time to actually bypass all these techniques which are there. So this is the roadmap of whole this world of overflowing, right? And I think one of the things, yeah, you see it happens till 1988. And for example, we have that Aleph 1 paper who documented it right in 96. And we have 97 Solar Designer, he is actually here, who actually wrote the first documented how to, you can actually take it like standard libc functions to actually execute what you want. So you can bypass like not executable stack and such things. So I have great responsibility actually to talk in front of him. Sweating here. So as you can see, he already have hard questions because one of the things he's also author of a John the Ripper. That's why he asked a lot of crypto questions. And I invite you to listen to his talk as well. And later, of course, we have here many progress. One of the most interesting things are actually this one, which return-oriented programming. It's just an evolution of this technique where you actually take just few instructions, let's call them the gadgets, to make your code actually execute. And you just take existing code where it happens inside the memory you already have, you don't have to craft your own, right? So it's like a little Legos you join and then you execute, right? Yeah, it looks complicated, but the most interesting, actually, I put one here. It's actually read to libc, and then with ROPs we have here, right? So, anyone dare to explain this one? For me, no? Okay. In short, what I already told you, its idea is to find instructions of, if you already have that vulnerable program and you just find those instructions inside, and then you find something that will, for example, set something like a variable, actually register here, whatever you need it, and then just to call some kind of a function there. So it's small Legos which you do like, and you just reuse existing code which is already inside vulnerable application. I guess this is the thing, and the problem is how we can prevent it, right? So you still have stack is not executable, right? And there is still exploitation going on. So I guess it's still relevant. I'm talking about even the stack overflows. I'm talking about the heap overflows. It's still happening, right? So the problem here is you can just reuse existing code and then do all those things, right? So if you look on the defensive side, here is many like security mechanisms embedded inside Linux. I didn't wrote it, Ofri done it, but you can guess which one Pokemon here is or not. It's actually no, it's every like every protection is here, but it's still missing some things. For example, here Linux had a pointer authentication here implemented. It's not here. Here we have, for example, shadow stack, which I mentioned, but it's actually not here, right? So it's good for a good summary, but it's still missing some of these things. So I will just give you a brief overview of which are most important here. So we have that now execute, which I already told you, address space randomization where addresses are different. I guess this part, I guess you know. Pointer authentication. Here we have that branch and shadow stack, but in ARM. Control flow integrity also in ARM. And now we have here indirect branch tracking and Intel shadow stack. So these two are actually quite interesting because, as you can see, it didn't have anything here on Intel, everything actually happened much more before on ARM. Do you think why? Because of the mobile phones and the mobile, Google just implemented most of these protections, and ARM already had support for it. It took some quite time to actually get those things merged in, right? So you can see this one happened just, I don't know, 3 months ago, that we had it in the kernel, but it's still not whole story, right? So protection is actually also taking some kind of a pace up. And about what we are talking about. What's that shadow stack at all, right? You have standard stack, right? I don't have to explain too much. You are most of you understand basic for flow stack and layout. It's just another stack where only return addresses are stored. And it's on different region of the memory. And then if the program comes back, before it comes back, it checks if that shadow stack is same as on the, for example, on the stack itself. If it's different, then control flow protection exception happens. And of course, then it detects it, something is wrong and it terminates, right? What is idea here? Idea here is if somebody messes the stack, return addresses, this detection will find it and it's embedded inside hardware. So how it actually looks, there were also for Intel, there were also implementation, just pure software implementation of that technology without hardware. You can do it as well, right? This is, for example, basic instruction. This is how it looks like if you compile it just under one. And this one is if you compile it with shadow call stack sanitize, right? And you can see they just use one register to actually store where another one copy of this stack is located, and then just compares it if it's the same value when it's returning, right? As you can see, this is only software implementation, but it gives you an idea how it looks like on behind, right? And interesting thing here is that hardware-based, of course, have better support, right? So why they dropped just software support? This is from a Clang official, like a patch, why they remove it. It's because of the performance. For example, they tried to compile Chrome and they had like a 13% of performance issues, as well as problems where you can still, if it's everything in software, you can still do some kind of bypasses and so on. So it wasn't so good. So they just dropped it. So there is another chance, right? If they implement it in hardware. So this is where it started. And idea is actually that you have CPU with that support, but you still need to have all those stacks there. It's not enough that you have that hardware and it will automatically work. You still need to have kernel which knows which register to set. You still need to loader which will actually say, okay, this one have this protection. You still need to have binary which understands this one. So for the hardware part, you need CPU with support for shadow stack. As I told you, probably CPUs built 2020 and older. And that's probably Tiger Lake or later. And usually you should read somewhere that it supports Intel control flow reinforcement technology. Actually, indirect branch trunking and shadow stack, it's actually, these two technologies are actually part of Intel control flow enforcement technology. So once you have hardware, how you know it's supported? Well, this is one of the ways. One of the ways is actually that you check CPU ID and check for those things inside. If you dig deeper, how you can actually check it, you actually call that CPU ID instruction, and then you just check specific bits here. Here you can see official Intel documentation, and here is implementation of that checking. Why not proc CPU info? Any Linux guru here? Why you would not check CPU info for this? Why we are looking at CPU ID? Okay, let me give you a cue. So these two things actually proc CPU info on the same hardware, different kernels. You will see that on this one, you have this little red flag, right? But on the left one, you don't have that one. Why? Because kernel cannot check that. It doesn't have support. So if you're trying to look on which hardware you will run and you still don't have kernel which is supported, you will not find it here. So that's why CPU ID is much safer to look, right? If you go through other steps later and you find out that your CPU is not supported, then you have lost your time. That's why I'm here, to not waste your time. So as you can see, you actually need kernel which supports this. That means you need like a 6.6 or higher, and you need to, of course, compile it with this option. And yeah, and then this will show up in proc CPU, right? And most interesting part is this is not protection for kernel. So kernel modules are not protected, only user land. So that means user applications. Yeah, now you know, right? So if you see this, that means you have two prerequisites ready, right? You have here hardware and kernel support, and that's it, right? ShadowStack is working. Not there yet, right? Why? Because the kernel says, hey, I can enforce ShadowStack, but only if loader tells me. And loader is not part of the kernel, it's part of the glibc. So here we have another release of glibc, just released, let's say a month ago. And which actually supports that. So the idea here is actually that it can tell the kernel this process can run as a with the ShadowStack option. So that means it only supports 64-bit because the kernel also supports only 64-bit. And you have to put all those options and so on and so on. So that means probably your favorite distribution currently does not have this. And changing libc, I don't know if you've ever done it, it's pain, right? So I guess probably you will wait for a next release or something. Or if you want to play, I have some scripts and to compile of this and actually have some kind of playing ground, which I can, of course, share. So you need to put, of course, new libc. So I guess new distros will slowly adopt it. Currently, I didn't see any which have this support. I mean, with the kernel, libc, and other things which I told you. So that's why it's a good time actually to see what will break and what will not, and how you can actually turn it on, right? And you can actually, some parameters you can actually tune during the runtime. It's not everything there. It's actually same as IBT. So if you, of course, you can turn off completely. If you see some problems, you can put permissive, or you can say on and it will be turned on. Whether it's regardless of whether ShadowStack or IBT is enabled, it's same. It's just different here. Here is ShadowStack or IBT, right? So if you have all those parts, we are still not there yet. So why? Because glibc wants to actually check if this application have shadow stack, is shadow stack supported on this application. How it checks? You need to have ELF binary with specific flags. Of course, you can produce the ELF binary yourself, typing in hex code, but usually you will use some kind of compiler, right? And these are two options how you can actually produce such compatible binary. And after you produce, you can actually test it. If it's everything is here, you should have something like this one here. So for me, my experience showed that, for example, using this flag will not produce this feature, only if you use FSF protection. Why? I didn't dig into GCC source, but I went to there. So great. So how would you test it? I guess we try to trigger vulnerability, right? But did we trigger the right mitigation? Okay, not yet, right? We are hitting other buffer overflow security control mitigation one. Which one? Yeah, canary. You're right. So I guess if you want to test this one, you actually need to bypass the canary first, bypass the other things, and then come and test this one, right? And the other thing is, you have to produce some kind of a ROP chain, right? And the third thing is you have to check if this process is actually having that protection inside. So let's see. By looking at the kernel documentation, you will see that you should have like a thread features turned on, right? And here it should show up something like some options like a shadow stack. It's not there. Well, then you dig up, look at the documentation, look at the commits, and then you find a wonderful commit which says, oh, we didn't enable it by default. You have to use tunables because we don't know if everything will work. And it's interesting thing that some Linux distributions already started compiling with that option, with one here. And actually, once this kernel comes, it will automatically get this, but we don't know if it will work because so far there wasn't glibc kernel, everything ready, right? You had binary and the hardware, but nothing in between, so it didn't work. So that's why unexpected things will happen, right? Probably someone who is system administrator, something will stop working. And for some other things, it's probably if you exploited something, maybe in the future it will not just work and you will wonder why, right? This is one of the answers, right? So what that means? That means you actually have to like set this tunable parameter and then run this one, right? In this case, you can check actually the process status and you will see there is like a lot of those things I just grabbed for thread features. And if it says something like this one, you have it enabled, right? Now you actually know you're running. And now you try the ROP, right? And what you get? It's working, right? You get the segmentation fault when you trigger it, right? So it's happy when you try it as a blue team, it's happy when you get this one as a red team, right? So let's talk a bit about compatibility. As you can see from all those things which need to be in line, legacy applications are not getting security for free, right? You have to do recompile them. You actually have to test them if it works, right? And it's a interesting process, but it will take some time, right? To get this into distributions, to test and compile, and something, of course, will break because compatibility issues, right? As you can see, it's 64-bit support only in kernel and glibc. I don't know if 32-bit will be supported. It's supported by hardware, but I'm not sure that they will implement support in kernel. It's long work, right? And I see Intel only submitted patches for 64-bit. Of course, you have to be aware that libraries and components, all parts should be compiled with Shadow Stack support. If it's not, then somebody can just take that part of the application if you have multiple binaries and bypass it by using just component which doesn't have protection, right? And virtualization, currently, although it's, let's say, it's in stable mainline, I couldn't get it working on virtualization. You can only have it on the physical hardware. Patches are still flying in. I see, for example, in last 2 weeks, there were some patches for QEMU and such things. So that means even if you're doing some kind of CI/CD testing, it's limited if you're not doing it on the real hardware with these options. If you want to check if you compile the right way and if it's working with Shadow Stack. So yeah, there are some limitations. And of course, the question is, hey, you are talking only about Intel, right? What about AMD, right? We also have those processors. They actually have the same protection. And what I read on the mailing list, I didn't write. For example, this APU, which have, for example, on Steam Deck, I couldn't get that they have like that support inside on APUs. I guess they're only having it on maybe on Ryzen's and such things. This is something that should be explored. But on there where they have AMD's Shadow Stack, AMD, it's actually, they said that they tested it and it works. You have to take word of this one. So the question is this end of the overflows now? I guess it's not. It's only even now more harder to actually exploit it, right? You have to actually now take much more time to bypass even this security control. You still have like a higher languages calling lower languages, lower language like modules and such things like libxml, lib something, right? And this is still the issue, right? And of course, the wonderful part is always bypasses, right? How this can be bypassed. One is, of course, find a component which is not protected. This is what I already mentioned, right? You have like all those things of the application must have those flags. If one of the libraries doesn't have, it will not turn on like a Shadow Stack, so it will not work. The other problem is, as you could see, there is a lot of dependencies. You have hardware, you have kernel, you have glibc, you have compiler, you have binary. So those all things actually where it can fail, right? So there's a lot of things and points where you can take a look and see if there's some problem. And of course, there are already some techniques from other operating system architectures, like, for example, control flow guard and such things. Those techniques, it's now when it's ready actually to try it, right? So ideas for research further if you're interested. Also, there are some implementation details which they document specifically, for example, where they turned off by default. So for example, user space decides somewhere wherever it will turn on or turn off. For example, exits is one of them. So these things are actually all those points where something can happen, right? So here are takeaway. If you're a system administrator, if something stops working in the next few years, check one of these as well. Because binaries, some of them are already compiled. When this just comes to glibc and kernel, it will just maybe something stop working. And here you actually can see what you need to do to implement yet another overflow security control, right? If you're a developer, now you know another new flag which you should add to your arsenal, how you should compile your, for example, your C++ applications or your C++ modules. if you're using Java, for example, GNI, or if you use any other like Python or whatever, and you're using those. So this is something that you should put it, right? And you know actually how now you should actually test it. If you just do it, compile it with those flags and run it on system which doesn't support it, the test is not good, right? And for those who are security specialists, you can actually see how to additionally harden your system, right? It really helps a lot in preventing ROPs, and how to check if hardening really works. You could see all those steps and how you can actually check on the end how this security feature will show up. And for the security researcher, I guess this will get you started to actually see what's there, how to get it up, and how to actually see if there's something to bypass or to actually make it better, right? Any other role you are in? Maybe I can make up some takeaway. No? Okay, so these are the references. I think the first one is actually the Intel Intel reference of the whole specification. You have IBT as well there. Here you actually have like implementation inside like a shadow stack, inside the kernel documentation. And you have here like libc branch, which was before official libc release, but now it's officially released months ago, so you can actually use it. Yeah, so I guess we can start with the summary. So getting shell, even if process is vulnerable, is getting harder. As you can see, there's a lot of those security controls, which helps. But we are still not ready yet, right? It's hard to say it's impossible after this one, right? Nobody can exploit it. The message is implementation is now complete. Now there's all those stacks in line. It just happened a month ago. Before, you couldn't do it. Only user space protection. So kernel modules and drivers are not protected here with shadow stack. All the applications, you have to recompile them for this one. And of course, if you have 32-bit or virtualization, currently it's flaky. It's not yet the default in your favorite distribution. So still recommendation best is fixing at the source of the problem, right? Another thing which I would like to summarize is actually here. I didn't mention too much about this one. This is only kernel protection, and this one is user land. It's actually, the best will be that there is like a kernel and user land, and here kernel and user land. And this one is actually only like a kernel land protection, and here we have only user space protection. So there's a lot of things going on that it happens on both levels. For this one, there is like a 30 different patches submitted to mailing list. Neither of these get in the kernel, only for the kernel protection. So there is no user space protection. And if your kernel compilation takes a lot of time, probably if you turn this off, it will take much quicker, but at the expense of the security features. So there is something, if you just want to speed up, you're testing some kind of a kernel, but in the production, probably I will dare that you leave this one as well. So these are actually all things which are needed for shadow stack. I didn't mention too much indirect branch tracking because it's not present in the user land, but I guess I just told you and mentioned you how you can actually get it. It's just there. So, any questions? Thank you. Any hard one? Oh, there it goes. Okay. Okay.
Enjoyed learning a few new things about recent developments that I haven't been watching those last 3 months. Like I said, that is cool. That's useful. Thank you.
Okay, I passed the test. Thank you.
Thank you. That's it.
If you need me anything or want to ask question later, I'll be here and feel free to ask. I didn't go to too much details, but okay, great.
Quick question. What are your bets on adoption rate? Because we saw a lot of like mechanism security-wise happening in Linux kernel. Like the most failed one, let's say SE Linux. What do you think is going to be adoption rate? Do we like you following this? Have you seen like there is a company that's already thinking of putting out a distro that like this has built in and precompiled all the stuff? Your thoughts?
Thanks for the question. So the question was the adoption rate of this security mechanism. What I see is actually other operating systems like Windows, they already have it. So it's a more competition. And I think it mostly depends on the Linux distributors, if they will push it or not. According to the features, because I see the other operating systems are using it, it's not that it will remove it from the hardware itself. So it only depends on the software. And I think if Linux distributors embrace it, and I see it's happening, I mean, they are still talking on the mailing list how they will implement it. I think that it mostly depends on them if they make it default. If they make it default, I guess it will go. But if other operating systems have it, I guess they have to have it as well. It's a competition. It's a good thing. Yeah, you're welcome. Any other?
No. So the lunch is served. Oh,
Okay.
maybe not.
Hard question is coming up.
No. It's if I'm not wrong, I think Windows has shadow stack protection only in kernel mode. Do you know if maybe Linux will? I think you said that in Linux it's not in kernel, right? Only user land. Do you maybe have any idea of progress?
I haven't saw it. I only saw for indirect branch, which like 30 patches and nobody takes care, like nobody cares. For this one, I don't know when it will happen for kernel. It's they just didn't put any like timelines or something publicly, so I don't know what's cooking. It's actually Intel writing those patches for the kernel. So maybe it depends also on them when they will implement this one. It's hard to say, but yeah, it's. I would like to see it more faster, but there is no any timelines. It's not a company, an enterprise, so. Yeah, but it's always option to write a page, right? You have the source.
Any follow-up?
Any? Oh. Hard questions coming again.
I have to work for you.
So we know that there's a shadow stack on Intel, right?
Yes.
On Windows, and we can defeat it with ASLR. What can we do to prevent those KSLR leaks and mitigate the options when you're leaking the pointers to the shadow stack? How can we mitigate those on Linux?
Again, I will dare to say thanks on the question. Again, I will dare to say at the source. So you have something called commem leak, which detects like info leaks. And this is one of the best ways. Let me just go here. Oh, it's this one. It actually helps in running it, right? There is like a Syscaller, Google, who is doing it for most of the core kernel part. but not for all the drivers. So if you're developing your own driver, probably you want to check with this one and test it. This would be the best on the disk, at the source level. For the other things, yeah. Don't display like leak addresses in logs. Usually it happened in Linux kernel as well. So if somebody have access to, like, for example, Damask, right? They could actually see sometimes if they can trigger some kind of unconditional or conditional, let's say, case where it will display some kind of addresses or dumps. It's where they actually get it. But now more Linux distributions actually turning off that user can access like logs from the kernel. But talking about logs about kernel, listen to Solar talk. So any other question?
No? Please clap your hands again for Vlatko. Thank you.
Yeah, thank you.